All right, this will be the video for AP Statistics, Chapter 24 and 25, which are taught together. This is about when you have two samples that are numerical, where you're computing a mean and you want to compare the means. And there's actually two ways to do that. One of them is covered in our textbook in Chapter 24 and one in Chapter 25, but we found that it's better to teach those together. So this lecture will cover those. And actually, for the most part, we have found that it's helpful to start with a little activity. So we're going to build in the activity into this discussion here, so you can participate at home. We're doing a modified version of the activity with the shutdown anyway, because even if we're back in person, we won't necessarily have the flexibility that we would normally do to be able to move around the room and pair up in different ways the way we would to do this activity. So the first thing to know is whenever we have two samples of numerical data where we're computing means, there's actually two different analysis methods. One's called the two independent sample hypothesis test or confidence interval method, and the other one is called matched pairs hypothesis test or confidence intervals. To see how this works, we're going to look at a made up example medical experiment. That'll show us the difference between the two, and then we'll kind of switch back to more traditional note mode, and we will look at the mechanics of what we write to conduct a hypothesis test or a confidence interval and how things like conditions change and all that. All right. So this first thing is referred to as the cholesterol activity, and it has to do with imagining that we're conducting a test for a new cholesterol medicine and comparing it to a current cholesterol reduction level medicine. So we're going to conduct this using theoretically a group of patients with high cholesterol. And if you look at that, there's actually many sources of variation in how the treatment will work on each patient, right? There are some factors that are different for each patient, like their initial cholesterol level or their age or their weight. And all of those things could potentially influence how effective the particular drug treatment is to reduce that patient's cholesterol. The treatment itself will have some effect on cholesterol level due to its actual effectiveness as medicine, but that effectiveness could potentially be different for each patient, right? Each patient might react differently to medicine, right? It might be more effective for some patients, less for others. And then the exact amount that the treatment improves the cholesterol is likely going to vary randomly a little bit from patient to patient, because whenever we do something in the real world, it's not exactly the same every time, right? So we should include something in our activity here to model the randomness that usually occurs. Okay, so we're going to include some way to model all three of these sources of variation that might affect the outcome in our experiment that we're modeling here. Okay, so we have to identify some subjects. Here are some example patients. They all have high cholesterol. Cholesterol is supposed to be around a number that's around 100 or below. So these people all have high cholesterol, sometimes very high cholesterol. We just have the subjects numbered from 1 to 20. They have different ages, different weights, and then initial cholesterols. Okay. So before the experiment starts, we collect data. We hope that this set of 20 patients was randomly selected and that they're representative of the population of all people who have high cholesterol. Okay, so now we're going to set up an experiment. And the first thing we're going to do is kind of a standard randomized design, right? The standard randomized design would be if we had the 20 subjects and we randomly assign them to two groups, 10 patients in group one, 10 patients in group two. And then one of the groups will give the new treatment and the other group will give the current treatment. And then we'll find the average reduction in cholesterol for each of the two groups. And then we'll have to find some way to compare these two means with each other to see whether there was a better reduction with the new treatment compared to the old, let's say, or if there's a difference. Okay, so to randomly assign patients to the groups, I ran in a calculator random integer 1 through 20 repeatedly to put the numbers of the patients. So I have 20 patients, they're numbered 1 through 20. And I did something like this where I, seeded my random number generator, let's say, stored that in the math random probability feature. And then I went back to math and then probability menu and I went random integer 1 comma 20. You don't have to do anything here, but I'm just explaining what I did to pick a patient. So that's patient number 19. And so I put patient number 19 in group one. And I did that again. And I picked another patient. If I had repeats, I ignored it. And I kept doing this until I found randomly 10 of these subjects and they went to group one. And then everybody else was placed in group two. Okay, so I did that once before I wrote these notes. And these are the subjects that end up in group one. And these are the subjects that ended up in group two. Okay. All right. So then now we want to conduct the experiment. So we would actually give the treatments. Group one, all the people in group one were given the new drug, and all the people in group two, I'm sorry, all the people in group one were given the current drug, and all the people in group two were given the new drug, the new treatment. All right. So I've got a spreadsheet here that kind of shows what happened. Here's all the subject numbers and their ages and weights and initial cholesterol level. And so we're going to compute the total amount of reduction in cholesterol that each patient had. And we want it to be a factor, we're simulating here, we want it to be a factor of all the different things that might cause variation. So the total reduction definitely is going to be due to the drug, right? And we said that every patient is going to have some difference in their response. So I have some random numbers here that represent these patients. This just reflects random differences in the people, how they respond to the drug. Okay, so regardless of which drug would happen, it'll be more effective in some patients and less effective in other patients. And this was randomly assigned like this. Okay, now since we're simulating what's happening here, I'm going to actually make it so that the new treatment has 10 points of reduction more than the current treatment. So in fact, the new drug is actually better. The amount of cholesterol reduction is 10 higher for the new treatment than the current treatment. So all the patients that got the current treatment, I put zeros in here, and all the patients that got the new treatment, they got an extra 10 points of cholesterol reduction because they took the new drug, which in fact is better. Let's say we're simulating that situation. And then I wanted to put a little bit of randomness in just from side to side. So apart from the fact that each patient reacts differently, right? Just whenever you do anything in the real world, there's some randomness. So I put a normal distribution here of up to standard deviation 2 amount of this. So the way I did that was with random. I went math, probability, random, normal. And I took random normal 0, 2, which means let's put a little kind of noise into the analysis, right? Where we're going plus or minus, some amount with a standard deviation of 2. So this patient happened to randomly get 1.9 points less than normal. The next patient maybe got plus 1.64 points and so on. So that's what this is. This is a little bit of random noise entered in on top of their individual effects that would have happened no matter what, and the effect of the drug. The old drug is not quite as good as the new drug. And so the total reduction is just the sum of all of this, the drug's actual effect, how much better the new drug is than the old, the individual effect of this particular kind of medicine on each patient, and then the random noise. And this is all the reductions that will resulted. Okay. So the higher this number is, the better the drug is working because we want to reduce the cholesterol, right? So this is cholesterol reduction. So the higher number is better here. All right. So now we can just look at these numbers, right? And this is where you come in. You can grab your calculator here. And we just want to find the average amount of reduction for the patients who took the current drug and compare that to the average amount of reduction for the patients that took the new drug. So what I'll ask you to do is to put all these numbers in your calculator in list 1 and these numbers in list 2, and then use one variable stats twice to find the mean cholesterol. Just decide for yourself, do you think the new drug's better? And I'll do that over here too, so you can see the steps, but try to do it on your own. We're going to enter the data for the group 1 into list 1. And the data for the amount of reduction in group 2 into list 2 for each patient. Then we can run one variable stats by going stat and then over here one variable stats and selecting a list like list 1, second one. And then we can record the mean, which is 50.4. So the people who got the existing drug had an average cholesterol reduction of 50.4 points. If I look at the same thing for the second list, the people who got the new drug, that turns out to be 68.7, which is quite a bit higher, 17 point something points higher, 50.9 compared to 68.7. So the question is the new drug better? Well, definitely the average cholesterol reduction is higher in the new treatment than in the old, right? If we were conducting the experiment, we wouldn't know all these values. We would just have these values. So we would have to just compare the means. So maybe you'd say, well, that's higher. But the question is, we don't really know how much we should expect the means to vary, because we wouldn't expect in two groups of people the means to be exactly the same. So is that difference in means statistically significant, or is it just random and would easily occur by chance? So we have to consider that in comparison to the standard deviations. The difference between 68.7 and 50.9 is 68.7 minus 50.9 is a difference of 17.8 points. But if you look at the patient-to-patient variation here, anywhere from 9 to 100, that seems like not that big of a difference when you have differences from 9 to 100 just from patient to patient who all had the same treatment. So maybe that's not statistically significant. In fact, if you wanted to kind of look at it, you could maybe do a dot plot of all the individual cholesterol improvement numbers for each of the people who got the current treatment and for each of the people who got the new treatment. And you could calculate not only the mean, but the standard deviation, the sample standard deviation for each, and say, yeah, the average here was 50.9, but there was a standard deviation of 29. There was still a lot of variation from patient to patient. And same thing here, the mean was higher, was 68.7 with the new drug, right? But the standard deviation is very high. So the real question is this difference in means here, this difference right here, is that statistically significant? And it's hard to say that it is when there's so much variation. This difference in means is less than, it's like a half of the standard deviation. So it seems like it's very statistically significant. And we're going to find out, in fact, that it would not be statistically significant. That's well within the normal variation you would expect just from patient to patient. And that's because there's so much variation in the results from the patients. Okay, so doing an analysis like this is called finding the difference of the means. It's treating each sample as a separate independent sample and computing each mean and then comparing the two. All right. So there is another way to analyze data like this, but you have to decide about this before you even conduct the experiment, really. The new drug, it did have a higher mean reduction in cholesterol than the old drug, but the difference was swamped out by this patient-to-patient variation. If we could find some way to reduce the amount of patient-to-patient variation, that might help us see smaller differences in the drug as being statistically significant. Right? So to remove sources of variation that are inherent in the subjects, we can use something called a matched pair experiment design. So in this case, what we're going to do is we're going to find some aspect of the subjects themselves, which might be having an effect on how well the cholesterol drug works for them. And then we're going to try to group the subjects into pairs where we try to match them as closely as possible on each aspect of the subjects. Okay. Now, in this case, we were told three things about each subject: their age, their weight, and their initial cholesterol level. So we're going to try to pick which one of those factors might have the biggest influence on how well the drug works. And since this drug is about affecting cholesterol, it suggests maybe the initial cholesterol level would be the one that would be the most important thing to control, to try to remove the effect of that from patient to patient from the analysis. So let's do that. Let's pick initial cholesterol level. And the way we remove it is we reorder the patient list, but by initial cholesterol level, from the lowest initial cholesterol to the highest initial cholesterol. Okay. And then what we're going to do is we're going to try to pair up. We're going to try to pair up the subjects in so that they're matched with someone who is as close as possible on initial cholesterol level. So we'll pair these first two together and form pair one, then the next two, and the next two, and so on until we have the last two, which are the two highest cholesterol levels. So each one in the pair is essentially paired up with another person like that, right? And I'll try to show you what a block diagram looks like for this at the end, a design diagram. It's tricky to draw. So we pair up on that initial thing. And then the way randomness is used is we still have to involve randomness. So we take each pair and then we randomly assign one of them the new drug and the other one the old drug. So what I did here was I used a random number generator. And if I got an even number, then I gave the new drug to the second one in the pair. And if I got an odd number, I gave the new drug to the first number. So in this pair, the second person got the new drug, and this pair the first one, this pair the first one, second one, first one, second one, first one, first one, second one. All right. All right. So then we apply the treatments, and that means in each pair, one of the people is getting the new drug and one is getting the old drug. Okay, of course, we're using placebos and stuff, so, or whatever. We make sure that the new drug, the old drugs look the same so that they can't tell which one they're getting. And that means, for example, this current person, which is part of pair one, right? Since they got the current drug, they have 0 for how much better, but the new drug, this person actually got 10 better. And what I did to keep everything the same was I kept the individual effects the same and the random effects the same, so that the only thing that's different is how we're doing matched pairing here instead of independence. Okay, so each pair, we calculate what their total reduction is for each individual patient. But then we do is we take each pair and analyze that pair. So within this pair, we're going to calculate something new, just a single number for the pair, which is the difference in effectiveness. So we'll take the total reduction for the new patient and subtract the one from the current drug patient. So for example, in this first one here, right, the new patient was this one, which was 19. So we're going to take 19 and subtract 9 to get that in this pair, the new drug worked 10 points better than the old drug. Okay, and then we do the same thing for this pair. In this one was the new drug. So if we take 27 minus 4, the new drug worked 3 points better in this pair, and so on. In this pairing down here, right, the new drug was this one. 110 minus 100 means that the new drug worked 10 better. And so now we don't have as many data points. We have half as many because we're pairing these up and generating a new data point just for the difference in how much better the new drug worked than the old. But now we have these 10 numbers that reflect the differences. Okay, so each of these is a difference. How much better did the drug work in that pair of people? So now if we were to analyze this as a data set, what would we get? So to do that, we're going to use a new list. Let me use list 3 now. And this time it's going to be the differences, right? So I'm just going to type these differences in directly. And you can do this as well. And then tell me, do you think the new drug worked? So 10, 3, 6, 14, 11, 9, 1, 6, 8, and 10. Then if I run one variable stats on that list, on list 3 of the differences, I find that the average difference was 7.8, which means on average, the new drug reduced cholesterol by 7.8 points more than the old drug, which is pretty close to what we really did, right? The drug was in fact actually 10 better than the old. With our first test, we weren't able to see that difference. But now, right, now I'm able to see that difference because even though there's still variation from patient to patient, the numbers are only varying from a difference in total cholesterol from 1 to 14. And the average is clearly above 0, which means that the new drug is likely better than the old drug. The main reason, though, isn't really because of the particular numbers. It's because of the fact that this standard deviation is so much lower, right? When we did the standard deviation calculations back here, right, the standard deviations was really high, up around 30. So this was still a difference in this mean of, over 17, but it was hard to see that as statistically significant when we had a standard deviation that was 30. That was like 2 to 3 times bigger than the difference we were seeing. But by doing this match pair, we effectively removed the effect of this initial cholesterol. There's variation from patient to patient, and we effectively subtracted it out of the analysis by computing differences in pairs of people who were identical or close to identical in that one factor. So we've effectively eliminated that from affecting the result. And now we have a lot less variation from patient to patient. That allows us to see this difference of 7.8 as significant, because it's now this difference, we're talking about the difference between a difference of 0. That 7.8 difference is much larger than the standard deviation. So the reason it works is because we're pairing up the subjects based upon initial cholesterol, that we effectively remove that factor from the experiment, which dramatically lowers the standard deviation. All right, so that's called a matched pair design. And it's a different way to conduct the data and a different way to analyze the data because we're working with just a single value of the differences. But this is only going to work if you match on something that actually affects the outcome, right? If you happen to pick something which doesn't have an effect on how the drug works, then this won't work. So let's say, for example, we thought age was the thing that was most important. And so we decided to line up all of our patients by age and pair them up that way by age, similar age. Okay. If you go through that analysis, you'll get these differences. You can carefully pause the video and look at all this or look in the notes if you want. And then if we type that in to a calculator, you're going to find that the standard deviation is 13.8, which suggests that the new drug is better, but the standard deviation is really big again. It hasn't reduced at all. It's still 29. So even though this mean is up here at 13.8, the standard deviation is practically 30, which means that it could go well down in here into the negative numbers, which means that the old drug would be better, right? In fact, if you look at where all the individual patients landed, we had values where the new drug was as much as 47 points better to the new drug being 30 points worse, right? So this data would not show that the drug was more effective than the old drug, because the no difference case is well within this span of variations that we had. The results are all over the place. Matching by age didn't work here because it didn't happen to be a factor which affected cholesterol reduction, right? Um, and because we didn't subtract out the variation in initial cholesterol, that more important variation is still left in the data. The way you can tell whether you have done matching on the correct thing is if this standard deviation succeeds in dropping, right? So just comparing the two, right? When we did matching by age, right, the standard deviation wasn't reduced. So this didn't show something that's significant. Zero, the difference of zero is well within the range of being possible. But when we matched by initial cholesterol level, the standard deviation dropped dramatically. And we had so much less variation, the standard deviation is down to 4 here, that this difference is statistically significant. That difference there is away from zero is statistically significant compared to this smaller standard deviation. So that's the point of matched pair designs, to remove a factor by pairing up that factor. Okay. A couple things to know about it. Since there's these two methods, you can't just arbitrarily pick one. If you're designing the experiment and conducting the experiment yourself, you have to decide ahead of time what you're going to do, because as you can see from the example, it changes how we conduct the experiment, right? If you're like in an AP stats class and you're just being given data and you have to analyze the results, then you have to try to discern whether or not there is some element where we should be matching. In other words, is the data connected in some way? Is there, if you have a list of data, like you have a data set 1 here, and you have a data set 2 over here, you have to ask yourself the question, okay, there's some data here, there's some data here. If I look at this value right here, is that connected in some way to this? Is it matched in some way with the value in data set 2? If it is, then you're required to do a match pair analysis. But if this is just some subjects and that's some subjects and there's no connection between these, then they're definitely independent and you're required to do the 2 independent sample analysis. So next, we're going to actually look at the steps for performing a hypothesis test or a confidence interval. We're going to find that the conditions are different depending on what type of data we're dealing with. So the first question we're always going to ask when we do an example problem is, what kind of data are we dealing with? Okay. All right, so this is more like the way the problems would be structured in the class, because we're not going to actually conduct experiments necessarily. Okay, so I'm actually going to compare the two things we just learned, the 2 independent sample means test, which was the first thing we did, to the match pair test. And then we're going to also compare that to the chapter 23, where we're comparing just one set of data to a historical number. So we'll look at 3 different problems side by side and just step through the analysis. Okay, so the chapter 23 that we were looking at before might be a problem like this. Historically, US adults have a mean cholesterol level of 190. The cholesterol level of a random sample of US adults are taken. Does this sample give us reason to believe that the cholesterol levels are now higher than the historic value? And in that case, we're going to be doing a t-test on that sample mean compared to the null hypothesis value of 190. Okay. Okay, now what if we had two different samples, but they were stated this way, something like this. A drug company has developed a new drug for reducing cholesterol levels. To test this, the company gives the drug to subjects and a placebo to subjects, each randomly selected, and compares the mean cholesterol reduction between the groups. So there's nothing in this wording to indicate that we were trying to pair anything up. We were given no information about the subjects and where we might have indicated that they were paired in some way. So I've got some numbers here related to the cholesterol reduction for the people who took the drug and a cholesterol reduction for people who took the placebo. But when I look at this list, I don't see any obvious way, say, to connect this number right here with one particular value over here, right? There's no matching going on here. So this is going to be a two independent sample means test. That means we're going to calculate a mean for this drug group, and we're going to calculate a mean for the placebo group, and we're just going to compare the two means like we did at the beginning of that activity. So because this is comparing two means with each other, this is sometimes called a difference of means test. And if we're doing this in a calculator, it's going to be the two sample t-test, kind of like the two sample proportion test that we did, where we had two samples. On the other hand, if we have something that's like this, we have a drug company has developed a new drug for reducing cholesterol. To test this, the company matches pairs of subjects by initial cholesterol level and randomly assigns the drug to one subject and placebo to other in each pair, then computes the difference, the drug performance minus the placebo, to see if there is a positive difference. In this case, we're going to take in each pair the value from the drug and the placebo and subtract them to get the differences. So therefore, we'll be back to having only, this is for the drug, right? Now we're going to have for each value a difference. These are all differences. And so this is going to be the mean of those differences. We're now down to just one data set, and it's the data set of the differences. So since we're computing a single mean of those differences, this type of test is often referred to as a mean of differences test. This one's a difference of means. This has one mean, this has two means. Okay, so the data would look different, right? In this case, we would have raw cholesterol numbers to compare to 190. In this case, maybe I would have cholesterol reduction numbers for one population or one sample versus reduction numbers in another. And in this case, I might be given those independently, but I would have to subtract them to get a differences column, right? Okay, the statistic. So in the chapter 23 type of problem, which is this kind, the statistic was the mean in the data. So we would have to enter the data, find the mean, and find the standard deviation, right, by doing one variable stats. This two independent sample means or difference of means test is covered in our textbook in chapter 24. And just like the proportions case, we're going to have two population samples, right? We're going to have a sample for the drug group where we could calculate the mean and standard deviation. And we're going to have a sample from the placebo group where we can calculate a mean and a standard deviation. And then we're going to form the difference, but it's going to be the difference of the means, right? So it's going to be probably better to write it like this, so it's not as confusing with this. We would take the mean of the drugs group and the mean of the placebos group, so 62.2 in this case and 56.6, and get that the average for the drug group is 5.6 points higher than the average for the placebo group. But on the other hand, if we're doing a match pair test, which is covered in the book in chapter 25, then we would be dealing just with the differences. So we're back to having a single mean. The differences, it's the mean of the differences. And the mean of this would be 9 with a standard deviation of the differences of 3.09. So the statistics are different depending on the type of data. All right. And then the hypotheses are different as well. So for a single sample mean problem, the null hypothesis would be that the mean is equal to the historic value, and the alternate would be the mean is greater, right? If we're wondering if the new drug is better or the people have changed in some way. In the two sample means test, it would be that the mean of the drug is equal to the mean of the placebo, and then the mean of the drug is greater than the mean of the placebo, or you could write it as a difference if you wanted to. But whenever you're doing a match pair test, you're required to always define the symbol D for difference and state what it is. D is equal to the drug minus the placebo for each individual pair, okay? And then that means that the null hypothesis, sorry, this should say HA here. The null hypothesis should just be the mean of those differences is equal to 0. And the alternate hypothesis would be the mean of those differences is some positive number, meaning the drug is better than the placebo. So 3 different forms of hypotheses. When we do the conditions, they're slightly different as well, right? We know that for chapter 23 type problem before spring break, right, we had to do, we have to know the sample was an SRS or representative. We had to know the sample was less than 10% of the one population. And we had to determine that the sample was nearly normal by looking at a histogram of the data, right? Or having a sample size that was larger than 30 so that we could guarantee that it would be normal. For the independent sample means one, we have to have, just like we did in the proportions case, we have to check the SRS for both populations to make sure both samples are randomly sampled from their populations or their representative. You have to check that both samples are less than 10% of their populations. Both samples have to be shown to be nearly normal. You have to check them both with histograms and or normal probability plots. And then we have the additional requirement that groups must be able to vary independently. So if we're doing an independent sample test, you have to believe that the variation in the drug group and the variation in the placebo group are not connected in some way. Okay, if we have a match pair test, we have SRS, a representative sample, for the differences, right? We have the data in the differences. So the pairs have to be representative of the population. And that sample size of pairs, which will just be N, has to be less than 10% of that population. And we just check the differences. Right here, you have to check both groups separately for nearly normal. Here, you only look at the differences. In fact, if you look at the individual ones, if they give you the individual ones, you'll lose credit on the AP test because you're only checking the differences, only working with differences here. And then there's a criteria that you have to state that the pairs are matched on some aspect of the subjects and state what that is. Right, so match pairs has a condition of requiring that they're matched in some way in pairs. Independent samples has a condition that the groups must be free to vary independently. So they're specifically not matched. So only one of these two analyses are going to be appropriate. You can't choose. It depends on the data, how it's presented, and how it was collected. All right, now the degrees of freedom. We know when we get to calculating p-value, we're going to have to use a TCDF function, and that depends on degrees of freedom. So for the one sample case, the degrees of freedom is 1 less than the sample size. So if the sample size was 10, then we would have 9 for the degrees of freedom, right? It's very complicated to calculate this for the 2 independent samples. That's because each independent person is free to vary, and they can vary to an infinite number of possible positions because, unlike the proportions case, it's a continuous distribution. So there's an infinite number of possible values. So this, believe it or not, is the equation for calculating degrees of freedom. It's based on the sample sizes and the standard deviations of each of the 2 samples. It's actually called the Welch-Satterthwaite equation. We will never use that, okay? And it often produces degrees of freedom that are non-integers. So if you actually were to take that data from this data set in this example and carefully plug it in and find what the standard deviations is here in the sample sizes and plug it into that, you would get 17.14 degrees of freedom. So this equation typically produces non-integer values here. In practice, we're going to always use a calculator. There's a way to get your calculator to force you to give this number if you need it. And often we're going to do these tests in a calculator anyway rather than by hand, and it'll display this value when we do the test. So just know that there's a very complicated way to compute this. And so often we'll just say we're computing this by calculator because it's way too hard to do by hand. Okay, in the case where we have a match pair test, we're back to just a single set of data. And if there's 10 differences, then the degrees of freedom is back to being n minus 1. So it's just 9. So degrees of freedom very easy for match pairs and also single samples because we have one data set that we're working with. But in the 2 cases, it's very complicated. All right. Then we have to calculate the standard error. Okay, so the standard error is S over square root of n for a single sample. We could take the S from the data, from the sample divided by the square of the sample size, we get 3.514. We can do the same thing for matched pairs, right? We use the same formula. We just use the differences. We just always are working with the differences. So we take the standard deviation of the differences divided by the square root of the sample size, 0.977. It's more complicated when we do the two sample case. And this formula is a lot like the formula in the two proportions case, where we just do it's based on this square root for the differences is the square root of the sum of the squares of 1 and 2. So you end up taking the square root of the sum of the squares. So you end up taking the square root of s squared over n for each of the samples independently. So you have to have the standard deviation of the drug set of data squared divided by the sample size plus the standard deviation for the placebo patients squared over the sample size. And that computes out to be 13.13 or 13.388. This is the reason why we have a condition that the groups must vary independently, so that this formula is working to combine things using those probability ideas. Okay, notice that the standard error for the matched pair test is typically quite a bit smaller than the independent samples, right? That is reflective of what we saw in our activity, that when you match pairs, you remove variation, right? Okay. Now that we have the standard error, we can calculate the test statistic, right? The test statistic for a one sample mean is that data mean minus the null hypothesis mean over the standard deviation of means. So if we had, this was just raw cholesterol numbers, 200.7 is the average cholesterol in the group, minus the null hypothesis of 190 over the standard deviation is the t statistic is 3.002. Okay, for the matched pairs, it's similar. It's going to be just with the differences this time. It's the average difference minus the null hypothesis difference, which is usually 0. It's actually whatever the null hypothesis difference is, but almost always, in all but one problem I've seen on the AP test, that's 0. And then divided by the standard deviation of the differences, which is 9.212. So many more standard deviations above the mean. And then the two independent samples case, you're working with the differences, but it's not the mean of the differences, it's the difference of the means. So this d hat is really the difference of the two means. And so that statistic is we're going to subtract the null hypothesis difference, which is that there's no difference, divided by the more complicated standard deviation of the differences. And so that turns out to be 0.418. So as you can kind of see, right, this is going to be statistically significant because it's 9 standard deviations above the mean. So is this one, but this one's not going to be, right? Because there's so much variation here. It's hard to see difference as statistically significant with so much patient-to-patient variation left in. So always better to do a match pair if you have the ability to match on something. We only do this if we can't do something better. Okay, and then the p-value calculation, at this point, very standard. We use a TCDF function. In this case, it's from the test statistic 3.02 to infinity with degrees of freedom 9 labeled, and that's 0.0075. For the two sample one, same thing. We do the sketch. 0.418 was the test statistic to infinity with 17.14 degrees of freedom, which is a p-value of 0.3406. And then for the match pair test, it was a test statistic of 9.212 to infinity with 9 degrees of freedom is 3.6 times 10 to the negative 6, so practically 0. So the conclusions would be written up as we always have been with alpha 0.05. P-value here is 0.005, which is low, so we reject HO. Since we are rejecting, we do have sufficient statistical evidence to conclude that the mean cholesterol level has increased. Right? In the two sample case, we would say with alpha is 0.05, the p-value of 0.3406 is high, so we failed to reject the null. Therefore, we do not have sufficient statistical evidence to conclude that the mean cholesterol reduction is higher for the drug than the placebo. Right? We have to use comparative language there, comparing one sample to the other. And then here we could say with alpha is 0.05, the p-value of almost 0 is low, so we reject the null hypothesis. Therefore, we do have sufficient evidence to conclude that the cholesterol reduction is higher for the drug than the placebo on average, right? We should probably put some word like that in there because we're talking about average differences. Okay, so that's the conclusions. If we're doing these in a calculator, there's tests for this, right? We use the t-test, perform a t-test in a calculator. what we entered, the mean, the null hypothesis was 190. We shaded to the right. And then when we write this, we always want to write down three things now. We want to write the test statistic that comes out, the t, the p-value, and the degrees of freedom. And in the t-test, it's not going to show that. So you'll have to manually compute this and add it in, that the degrees of freedom is one less than the sample size. Okay, when we run a two-sample t-test, that's for the two independent cases, we have to specify the direction, mu1 greater than mu2. Okay, we'll talk in a second why we're never going to select pooling. You do have a choice to select pooling, but select no for means. And then when we'll write this down, we get that the test statistic is 0.4183, p-value is 0.3405, and this will give me the degrees of freedom. And this right here is how we compute that. Rather than using the equation, we just go ahead and run a test, even if we're not being allowed to have the calculator behind the scenes calculate that crazy formula for me. Okay, and for the match pair test, we're back to performing a t-test again, right? Because we have just one set of data. These data are differences, typically in list 3, right? And we're computing against a difference. Now, the null hypothesis is not going to be a historic value. It's going to be a difference of 0. So typically in a match pair test, we do a t-test like this, but we do it with a null hypothesis of a difference of 0. We write the t-statistic, the p-value, and we record the degrees of freedom, even though the calculator doesn't provide it. Okay? All right. So that's how a hypothesis test is conducted. Let's move on to looking at a confidence interval, very similar. Let's say we wanted to now find a 95% confidence value for the values in the problem. We always check conditions. I'm going to go omit that because it's exactly the same for hypothesis tests, but always check them. That's important. Right? We're going to have to calculate the critical T star value like we normally do for the confidence level. So if it was 95%, the thing that would be different is you'd have to calculate it differently for each of these because the degrees of freedom is changing. For the one sample mean and the match pair, the degrees of freedom is 1 minus n, so it's 9. So we have 2.262 as the T star value for 95% confidence. Same thing here. But for this one, because the degrees of freedom is so much higher, 17.14, when we plug that in, we get a lower value here, 2.109. All right. And then we could, if we're calculating by hand, we'd use the formula, right? It would be the confidence interval is the mean plus or minus T star times standard deviation. We've already computed those from the hypothesis test analysis. And so we get that this is the confidence interval. And our conclusion is we're 95% confident that the mean cholesterol level for all adults is between 192.6 and 208.8. Okay, same thing here, except that for the two independent sample, we're taking the difference of means as the statistic, right? And then we're using the standard deviation for difference of means. So that computes to negative 22.6 to positive 33.8. So you want to always get the direction somehow in your any difference problems. So something like this for the conclusion, we're 95% confident that the mean cholesterol reduction for all adults taking the drug is somewhere between 22.6 points below and 33.8 points above the mean for those taking the placebo. Right. And then for the match pair test, right, we would be working with the differences. The differences was a difference of 9. Standard deviation for differences. So we have from 6.8 to 11.2, we could say we're 95% confident that for all adults, the drug will reduce cholesterol by somewhere between 6.8 and 11.2 points more than the placebo on average. And I like to insert the on average one in there when we're dealing with differences. We're talking about the average difference. Okay. And then, of course, there are also calculator functions for this. We could use the T interval for either the one sample case or the match pair case. The difference is that here we're talking about the interval for the actual cholesterol, the raw cholesterol numbers. And here we're talking about the differences, right? So this is the difference, how much better the new drug is than the old. And then we could perform a two sample T interval using that, again, no pooling. Okay. And then now we're talking about the differences. So see how this difference was statistically significant because all the differences always showed the drug was better. But this one had sometimes the new drug was worse and sometimes it was better. That was because we left all that variation in from patient to patient. So this wasn't as strong of a test. All right. I know this is a long video, but let's just wrap it up here. A couple things to note. When you do the two independent samples, right, it you can enter the data in either order. So like we could put the drug in list one and the placebo in list two, or the placebo in list one, or the placebo as the list one for the test and the drug. It doesn't matter, but that will swap which way this works. So you might have -22 and +33, or -33 and +22. You're allowed to swap these. You just have to keep track of the fact that the calculator always does list one minus list two. So if you have a positive value, it means that one is higher than two, whichever one you called one. So be cognizant of that when you use the calculator. Okay, and regarding pooling, back when we did proportions, we said we should always do pooling for hypothesis tests and never for confidence intervals, right? But the rule for means is we just don't do it. Just almost never. It's almost never justified. When we did this for proportions, we said that if we could make the assumption that the two population values are equal, P1 is equal to P2, or the difference is zero, then in the hypothesis test, that was our assumption, our HO assumption, and that allowed me to use pooled in the case of hypothesis, right? But in the differences, right, the standard error does not depend upon the means at all, right? The null hypothesis is going to be something like mean one equals mean two. And, if that was asserting that were true, we could claim that the populations were similar enough to be able to pool the results. But because the standard deviation here is not the same, it's not that. What we would pool only if we knew that the standard deviation in the first population is approximately equal to the standard deviation in the second one. And we typically don't know that. And our null hypothesis isn't stating something about the standard deviation. So the result is just don't pool, right? For means. Yes, pool for hypotheses for proportions problems, but not for means. No pooling for means. All right. Yeah. If for some reason you could, this is the formula you would use. You'd have to use this crazy formula for finding the pooled standard deviation. And if for some really crazy reason some question asks you about it, you could calculate this by faking this. As long as you know the sample sizes and the standard deviations, you could calculate that with this formula. Here's how you would do that. You can force the calculator to do that. So let's say I have some data where data one data set one has a mean. Actually, I don't even know the mean. Let's just say I know the standard deviation of this is 20 and the sample size there was 50. And I have another data set too, and the standard deviation on that was 24 and the sample size was 60. And I wanted to know what the pooled standard deviation was. We'll never use this formula, but what you can do is you can fake this out by saying, let's pretend to do a two sample independent test. So I'm going to go down here and do a two sample t-test in the calculator. Okay, and I'm going to enter stats so that I don't have to have actual data. I'm going to just set the mean to be anything, doesn't matter, call it 10. But I'm going to enter the standard deviation here for one, which is 21, and the sample size is 50. And then I'll just make up another mean here. It doesn't matter what it is. I'll just call it 20. Okay, but its standard deviation is 24, and its sample size is 60. Normally when you do this, doesn't matter what I do here, because that just affects the p-value. Normally you check no. But if for some reason you decide you're asked like a multiple choice question, it asks you for the pooled standard deviation, you can force your calculator to select pooled and then select calculate. And when it gives you the test statistic and the p-value and that crazy degrees of freedom, if you scroll down here, you're going to find that it adds on SXP. That's the pooled standard deviation. So you can force the calculator to give you this value here. All right. Very rarely does that happen. We'll never ask it on a free response question, but I have seen questions on the AP test on multiple choice where they've asked something like that. Okay, finally, there's one last thing to cover that's totally unrelated to this. Well, it's related, but it's something different. Our textbook includes this. It's, I think, sometimes not considered officially part of AP statistics, but it's called the Tukey test, and it's a fast, quick, back of the envelope way to quickly tell if you have two samples that are numerical, whether their averages are statistically significantly different. Okay, this was actually, it's not named after Awatuki. It's named after a guy named John Tukey, who's actually quite famous in signal theory and computing processes. He's actually the person who invented stem and leaf diagrams, box plots. He coined the word bit for representing zeros and ones, and he's responsible for an area of math called the fast Fourier transforms. He's actually a giant in the field of signal processing. But anyway, he said, you know what, this is a lot of trouble to go through when I can sometimes just look at the data and say, on average, this is much higher than this. So can we just get an idea of what the p-value would be without having to go through the whole thing? You're never allowed to do this on the AP test as your formal way to do a hypothesis test, but it's a quick way to get an idea. What we're going to do is check the condition. The only condition is if you have two sets of data here, then the min and the max must be in different data sets. So like if I looked at data set 1 and I scanned it for the lowest value, and that's 255, and the highest value is 300. And then I looked at data set 2 and its lowest value is 130 and its highest is 260. The only requirement to do this Tukey test is that the max has to be in one data set and the min has to be in the other. Okay. So then I just write this out like this. And then what you do is you say, okay, let's look at the lowest data set, the one that has the min. Okay. Then you look at the lowest value in the other data set, and you just count how many pieces of data in this data set are below that number, the lowest data set of the other one. So how many of these numbers are below 255? That one, that one, that one, that one, that one, that one, 6 of them. And you just write down the number. There's 6 of them below. And then you do the same thing on the other side. You say, okay, the highest value in this is 260. So how many data values stick out above that in the other data set? So how many are above 260? That one's right at, so if you have one that's right on the boundary, you count it as a half. So I have 1, 2, 3, 4, 5, 6.5. So I have 6.5 pieces of data sticking out here. And then you just add those two numbers up and get 12.5. And then there's this little chart. If that sum is greater than 7, then when you did a formal test, the p-value would be under 0.05. So if you get a number that's greater than 7, it means the difference in averages, the difference in means is statistically significant, which it is. This difference is whatever this average is and this average, there's a statistically significant average difference in the averages. If that sum is greater than 10, the p-value is actually below 0.01. And if it's greater than 13, it's below 0.05, 0.001. So this is quite significant. The fact that this is 12.5 means whatever the mean is here and the mean is here, whatever difference there is there, that difference is statistically significant because the amount of data sticking out on the two sides added up is greater than 7. Okay, just a little really quick rule of thumb that you can use to quickly determine if something is statistically significantly different. All right, that's it for both 24 and 25. So at this point, you should be able to work your way through some problems in the combined. There's one required practice packet for 24 and 25.